Today we'll be studying radioactive nuclear decay. We have already learned that some isotopes are unstable. Unstable isotopes contain extra mass and/or extra energy that result in the instability. These isotopes will lose mass and/or energy and decay until stability is reached. The process of losing the extra mass and energy is called radioactive decay. We'll look at today 5 types of nuclear decay. In this slide, we begin with alpha radiation. Here's the Greek symbol. Beta radiation, Greek symbol. X-rays, gamma radiation, Greek symbol, and neutrons. Let's talk about alpha radiation first. Notice that alpha radiation will not even penetrate a piece of paper. Beta radiation, on the other hand, will penetrate a piece of paper but would be stopped by a thin piece of wood or aluminum. X-rays travel through paper, would travel through wood, and finally would be stopped by lead, iron, or other thick metal plates. Finally, neutron radiation would travel through paper, through wood, or thin plates of aluminum, even through lead, iron, and other thick metal plates, but would be stopped by hydrogen-rich water or concrete. So what is alpha decay? Here we see an alpha particle. It consists of 2 neutrons and 2 protons. So basically, you would consider it a nucleus of a helium atom with an atomic mass of 4. When the alpha particle escapes, there is a decay in the original atom. We see a loss of 2 protons, so now the atom has a new identity. It's a completely different element. Also, this new element has not only a loss of protons, but also a loss of mass. So overall, this new element will show a loss of 4 atomic mass units when compared to the first element. This is alpha decay. Now let's look at beta decay. Beta radiation takes the form of either an electron or a positron, which is a positive particle with the same size and mass of an electron, but with a positive charge. These are emitted from the atom. Due to the smaller mass, it is able to travel much further in the air, up to a few meters, and can be stopped by a thick piece of plastic or even a stack of paper. Now let's look at gamma decay. Gamma radiation, unlike alpha or beta, does not consist of any particles. Instead, it consists of a photon of energy being emitted from an unstable nucleus. Having no mass, no charge, gamma radiation can travel much further through the air than alpha or beta radiation, losing on average half its energy every 500 feet. Gamma waves can be stopped by a thick, dense enough layer of materials such as high atomic number materials like lead or depleted uranium. These would be effective forms of shielding. Now let's look at X-rays. X-rays are very similar to gamma radiation, with the primary difference being that they originate from the electron cloud. This is generally caused by energy changes in an electron, such as when an electron moves from a higher energy level to a lower one, causing the excess energy to be released. X-rays are longer wavelength and usually lower energy than gamma radiation. Finally, we'll look at neutron radiation. Neutron radiation consists of a free neutron, usually emitted as a result of spontaneous or induced nuclear fission, able to travel hundreds, even thousands of meters in the air. They are, however, able to be effectively stopped if blocked by a hydrogen-rich material, such as concrete or water, not typically able to ionize an atom directly because of their lack of charge. Neutrons most commonly are indirectly ionizing. That is to say, they are absorbed in a stable ion atom, thereby making it unstable and more likely to emit ionizing radiation of another type. Neutrons are, in fact, the only type of radiation that is available to turn other materials into radioactive ones. So today we have studied alpha decay, beta decay, gamma radiation, X-rays, and neutron radiation. All of this radiation is achieved due to instability of isotopes. All isotopes will seek stability, and in doing so, they will emit this radiation.